It's my great pleasure to welcome our our guest speaker, Jonas Kübler, who volunteered to give a talk about a subject that's quite fascinating and close to our heart. In fact, as close to our hearts that we already had a journal club specifically on that very same paper, which is maybe a good preparation for the subject that's about to come. Maybe a few words on Jonas. I mean, he has a physics background, but is doing his PhD at the Max Planck Institute more on the computer science side of things, which is great because he's somehow between the worlds and not a completely dissimilar style as we often tend to be. So also the topic that he will speak about is on kind of a rigorous picture of what quantum machine learning may have in store. So as we all know, there's a lot of excitement about the idea that quantum computers may have applications in machine learning concerning improvements of generalization, of computational speedups, and so on. And of course, quantum kernels are much discussed in that context. And the paper he will discuss today is indeed about functions that are defined via quantum kernels, which offer lots of potential because we have exponentially large Hilbert spaces to operate with. But then the issue of generalization may be tricky. And what he will tell us about is like a highly, say, ironic and sobering experience along these lines. I don't want to anticipate the outcomes, so I will not say too much, but I can already tell you that it's kind of an interesting story on a rigorous approach to what quantum machine learning could or could not have in store. So thanks for coming. It's great to have you, and the stage is all yours.
Okay, thank you very much, Jens. I'm happy to give this talk today. It's a great opportunity. Also, I'm really happy that this work got some interest from the quantum community also, because arguably we're a bit in a machine learning bubble at our institute. And yeah, feel free to ask questions anytime, also at the end. So this work, you can also find it on the archive, and I did it together with Simon, who is a postdoc at the MPI. He's a mathematician, so that's great to work with, and Bernhard, who's my PhD advisor. Okay, so maybe to start off, a quick overview of what I'll talk about and also what I won't talk about, and maybe to set a bit this into context. So I think a lot of excitement in this quantum machine learning also regards the NISQ era of quantum devices, so near-term devices with noise, smaller scale. I'll actually not specifically talk about those things. So the considerations I'll present today hold even if you have a fault-tolerant quantum computer. Then the other thing in quantum machine learning is what kind of speedups do we consider? And I think a lot of, let's say, early work was on speedups of linear algebra subroutines. So in quantum or in machine learning generally, you use a lot of linear algebra, and there are these early algorithms like the HHL algorithm that allow you to obtain speedups in these linear algebra subroutines. I'm also not going to talk about quantum neural networks, if you want to call them like that, or variational quantum circuits where you have explicit parameterizations of your models. And since I'm not going to talk about that, I will also not talk about gradients, although I think gradients are something cool and worth talking about. And since the results are a bit, let's say, try to give a realistic picture and also maybe a bit of a sober picture, I'm also not going to present any results on real data because I'm not aware of any data set that makes sense to use with the quantum computer. So what I'll talk about is, first of all, large constraint. I will talk about supervised learning. And I will mainly talk about regression. So the task of fitting a function to data, essentially. And we'll do this with quantum kernels. And quantum kernels, we'll come back to that, are basically inner products of quantum states that encode some input. And the types of speedups I'm interested in are in terms of data efficiency. So are there tasks where if I define a model where I had a quantum computer, I can learn with substantially less data than I would need if I do this classically. And we will use some concepts from learning theory, and I will also show some illustrative toy examples. And maybe one last comment before we start. I think this data efficiency is a concept that has not been studied so long in this quantum machine learning field. And of course, it's also related to runtime, right? Because of course, I could simulate my quantum computer classically, but that takes a lot of runtime. But of course, then I would be able to learn as efficient as with the quantum computer. Okay, so that's just a disclaimer. And I'll actually start maybe the other way around than most people. I'll just quickly highlight my main messages here. So I think the first one is kind of a no free lunch type result, and that also holds with quantum computing. So the idea is basically that if you explore the whole expressivity of your quantum model, and this expressivity grows exponentially large, but you're not favoring any functions out of these exponentially many, then you will also need exponentially much data to reasonably learn something. And how can you get around this is if you have some prior knowledge about the problem that you're studying, and you manage to encode this into your quantum device. But if you cannot encode this classically, then I think you're on track to finding some advantage in your quantum machine learning model. And I think the last point that's also something that is kind of close to my heart is don't forget to measure, because a quantum computer is kind of an analog device in some sense. We need to make measurements and estimate quantities. And we need to estimate stuff very, very precisely if we're not careful. And if this precision is exponential, then we're also doomed because we need exponentially many measurements. Okay, now with that, let me start introducing kernels from a purely classical viewpoint. I think some of you maybe have heard about kernels, but I'll nevertheless give a very quick overview. And just for this overview, I'll actually consider the task of classification. So just imagine this simple data set.
Can I ask a question? I mean, maybe a meta question, whether we should ask questions along the way or better at the end.
I'm happy to take questions anytime. I mean, if it's being too much, then we probably make them short and so that I can go through everything I want to say, but I'm happy to take questions anytime. So if you think something is unclear or notation is wrong. Yeah.
Maybe a remark. I mean, the remark concerning measurement, of course, applies to any quantum algorithm in the sense that you necessarily have to have lots of entanglement in a quantum algorithm along the way. But before you measure, you should have really highly peaked distributions and very little entanglement. And like if it's too correlated, then the measurement messes up everything anyway in any algorithm. So in this sense, the machine learning type algorithms are not so special, but never mind.
Yes. Yeah. So I think one reason why I emphasize this so much, I think there's some people who think that if we can estimate something to precision epsilon, and epsilon is small, like 10 to the minus 3, then that's enough. But I think there are situations where the precision that you would need becomes like smaller and smaller, and then also you would have to take more and more measurements. But yeah, we'll come back to that. Now, why do we want to talk about kernels? So imagine you have this classification problem. Someone gives you data from two classes, and your task is now if someone gives you a new data point, you want to tell to which class does this data belong. And in this case, what you could say is, well, let me just fit some hyperplane, some linear hyperplane that has the largest margin between the two classes. If you do that, then you'll find that this is known as support vector machines. And it's a nice algorithm that you can run in closed form. There's no like numerical optimization needed. And basically all you need to know about the data is inner products within between the two data points. Can you actually see my cursor?
Yep.
Yeah. Okay.
Yeah. Mm-hmm.
Cool. Okay, but now let's look at this data set and you realize, well, there's no great hyperplane that I can use to separate this data. Okay, and so the basic idea of machine learning general or kernel methods specifically is to map the data into some higher dimensional space such that you have more freedom to fit functions and then train the algorithm in that feature space. Now for the specific example, let's just take this two-dimensional input and map it onto something three-dimensional with this rule. Then let's look at the data from the right angle and you see, oh, perfectly separatable, right? You could have guessed that from the initial picture already that you might be able to do that, but that's the way to do it. And now you can just train your support vector machine in this feature space. And again, all you need are inner products of now between your features, okay? And the data becomes linearly separable, and you have a more expressive model. Now let's look a bit closer at this feature map. So very specific example here to make it illustrative. Instead of going to the three-dimensional feature space and computing the inner product there, what we can actually do is we can compute the inner product directly in the original space and square it, okay? And let's just call this function k. It's basically a function that takes two inputs from the original domain and outputs a number. And now the cool thing is that we don't need to go to the feature space. Now, between R2 and R3, there's not such a big overhead, but imagine that your feature map is in like 10 to the 5 dimensions or even infinite dimensions, then you will have to use such a trick in order to harvest this expressivity. And this is known as the kernel trick. So if there's a cool function that you can evaluate and it corresponds to an inner product in some high dimensional space, then you can just use that function to run your machine learning models. Okay, so basically kernels are inner products in high dimensional feature spaces. I think that's most of we need to know today. And maybe some quick example here. I think one of the most remarkable or fascinating examples are Gaussian RBF kernels. So that's the kernel down here. It's basically just the exponential of some negative distance, square distance between two inputs. And it turns out, if you look at that, that's actually a kernel that corresponds to an infinite dimensional feature space. So if you don't know about the kernel trick, there's no way you can learn in this feature space, right? But if you have the kernel trick, then basically in linear time or without any overhead, you can learn in this high dimensional space. And I think it's also important to have always at the front of your head. Also in classical machine learning, there exist models that are extremely expressive. So even infinite dimensional, right? So purely to get expressivity, you probably don't need a quantum computer per se, right? If it's just a question about expressivity. I think that's important to highlight. Okay, and now maybe the question is like, what kind of functions can we learn with these kernels? And basically we can learn linear function. So yeah, if M is basically also an element in the same space, then it's just an inner product between the feature representation and some observable, if you want to call it like that. Or you can also write it directly in terms of kernel functions. And I think this notation also worth a look. So basically the kernel usually takes two arguments and outputs a real number. But if you fix one to X and leave one free, then it's just a function, right? A classical function where you put in an argument and you get a number. So this is indeed a function space, and this reproducing kernel Hilbert space is basically the closure of the span of all these functions that you can define via the data that you have.
Is the closure in any way important? Not really, right? I mean, you're anyway approximating.
Mm-hmm. Yeah. Don't forget about it. And as I said before, it can be infinite dimensional, and there's cool theory, namely the representer theorem, that allows you to, like, in most situations in machine learning, find solutions in a low dimensional subspace, and the dimensionality of the subspace only grows with your data set size. So that makes learning feasible, and you have theoretical proofs that you find the empirical risk minimizer in that space. Okay, maybe that's a good point. Just take a breath. Any questions about like classical kernels that you think? Yeah, I guess in your group, and also if you studied the paper, most people have seen something like that before. So I'll not waste too much time here. Now, people have said, well, inner products in high dimensional spaces, that's something we can do as well. And those people came from the quantum community. And so I think this whole field started like 2 or 3 years ago. And I just highlight these two papers here because, at least for me, those were the first papers that I encountered in this direction, one from Xanadu, one from IBM, that proposed to use quantum kernels. So what do we mean with a quantum kernel? And so I think a quantum kernel is basically a mapping, or is an encoding where we take a data point from our domain, from our problem domain, and we map it to a quantum state. And this mapping is something that we choose basically by design. We say, this is the model we want to use. Thus we fix this mapping, and then everything comes afterwards. And the quantum kernel is now again an inner product. So basically a Hilbert-Schmidt inner product between these density operators. Okay. As I said, it's in a product in exponentially large space. And remember, for later, we will have to estimate this for measurements. Although for now, quite a bit of the talk, I will actually ignore this fact that we need measurements. And again, like what functions can we learn? Now, for physicists, you would say M is an observable. And then basically you can define functions that are defined as the expectation of some observable depending on your parameterized state.
So sorry, when you say you ignore measurement, you say that you're basically taking Hilbert-Schmidt scalar products for granted, ignoring the sample complexity involved in actually estimating that dude, right?
Yeah, for quite a while actually of this talk.
Okay.
Because I think, like, to me at least, let's say the ideal case is where you can actually estimate this to arbitrary precision. And if we already find here some problems, then we don't need to pursue further, I think. And then the other situations occur where we don't find problems without the estimation, but then the estimation might lead to problems.
This kernel is 2 times quantum, in the sense that it's based on like a quantum algorithm, which is like this row, and then you estimate it using a quantum computer, which are 2 different things. Like there could be kernel functions that are inspired on these rows, but you can compute classically, and there could also be kernels that are not based on a feature map, but for which you use a quantum computer to estimate. Do we agree? So, I mean, what I'm saying is there could be functions of 2 variables for which you need a quantum kernel to for which, let me start again. There could be functions of 2 variables that have to be estimated using a quantum computer, which are valid kernels in the sense that symmetric, positive, semi-definite, blah, blah, but which cannot be written as the inner product of quantum feature maps.
Okay. Yeah. Yeah, I don't have any reason to believe that this doesn't exist.
Yeah. Do you have any reason to believe it will be interesting as a class of kernels?
So I mean, I think it's generally a bit difficult to like just simply write down a function of 2 variables and realize that it's a kernel. But if you can do that, I'll get it on a quantum computer, but not classically, I'm happy to work with that. Yeah. I didn't think much about it also, to be honest. Yeah.
Maybe we can talk about that later. I never heard that idea before, but I think it's super interesting because, I mean, people studied like Boolean function complexity of like symmetric functions and all sorts of things. And it's a place where people know a lot about like circuit complexities in different models and where you could like have a lot of concrete tools.
I mean, I think this is why we call them quantum embedding kernels in our QHAS paper, because they are like, they come from the point in the.
Okay, yeah, that's maybe a good point. Thanks. Let's discuss this later, or if you want that, because I think there's also a connection to like these quantum neural networks. At least if you have a quantum neural network that only has 1 layer of encodings, then usually you would have a fixed encoding and then some parameterized observable. But basically the RKHS contains all these functions. So it's strictly larger, or like not strictly larger, but at least as large, just in terms of expressivity. And obviously everything with kernels is easier to analyze than everything that has the word neural networks in it. So we do that. Okay, but now the important question is it all worth it? I mean, arguably, I would say if you're just up to like classifying MNIST data, then just don't use a quantum computer that works sufficiently well classically. Maybe also one example, maybe that's a bit like too easy for you, but just because that will be our running example. So for example, if we have only 1 qubit and 1-dimensional data, what we could do is just embed this data in a rotation, right?
No, that's great. Actually, we had a discussion like only 2 hours ago where we thought, oh, we need the 1 qubit example. So that's great. Thank you.
Okay, and if you do this encoding and you go through the numbers, then you find that the kernel is basically a squared cosine of the difference between these two variables. And what we will often also consider today is where our input is d-dimensional and we have d qubits, and every dimension of our input gets mapped to a single qubit. And we do this because I think that makes it easier to analyze. And I think that's also something that is really important when we think about quantum machine learning. We need to somehow specify how our problems and our kernels behave as d grows, because only then it makes sense to me to kind of talk about some, let's say, complexity advantages. Because for fixed problem, like, okay, yeah. Okay, and if you do this like every qubit with a single coordinate, then you basically just get a product of the individual kernels. And just also to emphasize this here, this kernel will never be super interesting because you can just compute this classically. But nevertheless, it's useful for illustrative purposes. Okay, and now I think that's probably something that caused already some controversy. I will tell you how to obtain a trivial quantum advantage for machine learning. And basically the idea is, suppose you have a quantum computer. That's actually an example of a non-kernel embedding kernel. So suppose you have a quantum computer that computes the function f somehow efficiently, just some function, but you cannot compute this classically, okay? And now you generate a data set where you basically just put some inputs x through this function, you maybe add a bit of noise, and that's your training data, and now you want to learn a function. Now, if you have this quantum computer, you can define a kernel simply like this, by taking the product of this highly complex functions. Now, this is not an embedding kernel anymore, right? So this is just now a kernel function, but it's clearly an inner product in R1. So it's a kernel. And now clearly, if you learn with this kernel, this is going to be extremely easy because kind of the kernel already knows the solution, okay? But arguably, the quantum kernel can learn with exponentially less data probably than if you use some classical device, because the classical device doesn't know where to search, and so you basically have to search in a really large space and you need much data. Okay, so that's cool. That's actually a non-embedding quantum kernel. Okay, that might sound a bit too simple, and you might say, well, that's like not interesting. So I think there was a nice paper also this year from the IBM group, the rigorous and robust quantum speedup in supervised machine learning, where I think actually the idea is surprisingly close to this trivial quantum advantage. Basically, there you have a problem that is super easy to solve once you can compute discrete logarithms. But if you can't compute discrete logarithms, then it's extremely hard to solve. And you know that the data is of this kind. And now they basically say, well, let's use a quantum kernel that basically computes the discrete logarithm for us, and then learning will be easy. I think that's a cool paper. But I think it's not, honestly, not conceptually different from this trivial quantum advantage that I have on top here.
But it's so interesting in that it uplifts problems of computation complexity of quantum algorithms to the learning realm, right? So in this sense, it is
exactly
doing something interesting.
Yes, exactly. So I think that basically implies that whenever you have already known complexity advantages, you can basically also map these to machine learning problems, if you want to put it like that. Exactly. Okay, and now let's focus on regression. I think surprisingly, most people usually consider classification in this quantum machine learning realm. I think actually regression is easier. Like also most of the machine learning theory work is actually on regression, I would say. And I think the reason is simply because there's no thresholding or anything like that involved. You can just have continuous things and you don't need to introduce thresholds. And a bit of notation. So I will always consider some input domain. That's basically the data that we have, images, whatever, in RD. And we will try to learn functions that map this input to a single real number. So yeah. And basically the problem is defined via joint labels. But we don't know this. We only have n observations. And we don't know the the empirical measure as dn. And something that is important for our analysis is basically the measure or the distribution simply over x. So forgetting about the labels or the y values, then we call this mu, and also define the inner product with respect to mu like that. And then the risk or the loss we're trying to optimize is the mean squared error. Okay, so if we have a hypothesis or function h, we give it a loss, and this loss is basically computed by drawing random samples from x and y, and then push x through h, and look how well does it agree with y by computing the square distance. We don't know the risk because we don't know the distribution. We only know the empirical distribution. So what we'll do is actually we'll optimize the empirical risk and then hope that the generalization error is small, such that the training error that we observe is a good proxy for the true risk. Okay, that's just standard supervised learning. And we'll do kernel-rich regression because that's what you do with kernels. And basically what we'll do here is we will optimize this empirical risk and we add regularization. So that's an important concept. So lambda is a positive constant that we have to choose. It's a hyperparameter. And then we will penalize functions that have a large norm in the RKHS. And we'll see a bit what that means. And the nice thing is that we can compute this solution of kernel-rich regression in closed form. Basically, what you need to do is you need to compute the kernel matrix. So the kernel matrix is just the n by n matrix of pairwise kernel evaluations. Then you add a bit of identity, you invert it, and then you multiply it onto your vector of y observations. And basically, what I will tell you now is like, when is kernel-rich regression easy to do? So easy in the sense of little data suffices. And we'll see that this will depend on the target function, the distribution over x, and the kernel. And I emphasize this because you might think there are good kernels and bad kernels, but there are only good kernels for some problem, like very specifically. So for example, the Gaussian kernel is great if your problem has some continuity, right? But if your problem hasn't this property, then the Gaussian kernel might be really bad. Okay, and so it's always an interplay between these things. Okay, and we will basically do a spectral analysis of this kernel, and then we'll compare the spectrum of the kernel with the eigenfunction, with the function that we are trying to learn. And for that, we will basically look at this kernel integral operator. The kernel integral operator is basically the generalization of the kernel matrix in the infinite data limit. So think of a normalized kernel matrix and then take the limit of continuity, then the spectrum of this kernel matrix in the limit will be the spectrum of the integral operator. So they are basically the same thing. And we can decompose this integral operator. This is a positive operator, and basically in an eigenbasis, and we will choose eigenfunctions that are orthonormal with respect to our marginal distribution. So mu, again, is the distribution over x, and we will choose the decomposition such that the eigenfunctions are orthonormal with respect to this distribution. And then we can rewrite our kernel function like this. So this is now a sum of weighted, basically with positive eigenvalues, and then just these eigenfunctions. And this is basically important because this is now a different form of the kernel than we had previously, right? Previously, we just wrote the kernel as an inner product of quantum states. But now we basically found a decomposition that is specific to our problem. Okay, so if you have a different problem, you will have a different Mercer decomposition. And something that we will assume throughout is that the trace, or mostly that the trace of this kernel integral operator is 1. And this will generally hold in the easiest case if just the kernel of x with itself is 1. And this holds, for example, for pure states, right? For a pure state encoding, k of xx is basically just the purity of rho of x. And if the state is pure, then this is 1, okay?
Jonas?
Yes?
So I'm not so fond with function analysis details. Why can we apply Mercer's theorem? Like how do we know that the operator has a point spectrum, or does it have a point spectrum?
Yeah, I'm also not such a great expert in functional analysis, to be honest, but I think it's a positive operator that is bounded or something like that, and I think that's probably suffices.
Yeah, I mean, yeah, bounded sounds pretty good, but
yeah. Because at least in our case, the kernel is bounded, right? If you think of quantum embedding kernels, they are bounded by 1. And yeah, I think this probably already suffices.
Right. If the kernel function is bounded, like if lowercase k, this little kernel function is bounded, then no, the operator should be bounded as well.
Yeah, something like that, I think.
Okay.
Yeah, but
Thanks.
yeah, I think, like, I don't know, interesting question. I think, at least in my training as physicists, I would always be like, oh yeah, sure, something like that exists. But it's good to ask. Thanks. Okay, and basically now the crucial thing is that we will have to decompose our target function. So f is always the function that generates the data, basically, in terms of this spectral decomposition of the kernel or of the RKHS. And if we do that, then the norm of this function, the L2 norm of this function, is just the sum of these coefficients, because these phi i's are orthonormal. But the RKHS norm, so the norm in the reproducing kernel Hilbert space, basically weights every coefficient with the eigenvalue that it has in the RKHS. And remember that our kernel ridge regression penalizes functions with large RKHS norm. So that means that if you have some part of this function that corresponds to a small eigenvalue, it will be really hard to learn that, because basically the way you design your algorithm, you will try not to learn such functions. Whereas if you have something that has a huge eigenvalue in the RKHS, it will be relatively easy to learn that, because basically even without seeing data, you would kind of favor such functions. And I'll introduce two qualitative measures that I actually not use later on anymore, but I think it's nice to kind of get some idea. So the first is kernel target alignment. I think actually some people in this call used this before to optimize quantum kernels also. And here basically the idea is roughly how well is the spectrum of the kernel aligned with the target function. So it's kind of a like cosine of an angle between your spectrum and the target function. So again, in the trivial case, if our target function is just a times phi and the kernel is just basically one-dimensional with the same feature, then the kernel target alignment will be 1. And all you need to do to learn is basically just learn this coefficient a. So it's just the estimation of one single real parameter, which is pretty easy. Whereas if the kernel target alignment is small, then it will be generally harder to learn. But this is, let's say, that's just qualitatively. It's not strictly so easy to derive from the kernel target alignment how well it will work. Similarly, task model alignment basically tells you how much of the signal of this target function is captured in the first I principal components, basically the first I highest eigenfunctions. And also here, if I think especially if this is low, or if this slowly goes to 1, then learning will be hard, because you have to consider basically like everything in your spectrum in order to learn the function. Whereas if this is 1, then you can hope that if the eigenvalues decay fast, that it's easy to learn.
And
yeah,
slow and fast,
just,
poly versus exponential, I suppose, in the decay of the spectral values.
Can you say it again? Sorry.
I mean, like slow and fast presumably means like exponential versus poly scaling of the spectral values, or is that?
Yes. So for example, if you need exponentially many components of your kernel to approximate the function,
yeah,
and you will also need exponentially much data. Yes.
Okay. No, sure. Mm-hmm.
Yeah, roughly.
Understand.
Okay, so maybe also here a quick pause for questions. Again, I want to emphasize that basically a good kernel depends on the problem, and we'll use this spectral decomposition. So basically we will use properties of the limit of the kernel matrix to then talk about whether learning is feasible or not. Okay.
I would just ask, but this way of thinking about this phi, like I understand what they are from the definitions, but as a function, why would I care about it if I didn't have the definition? Like, or how can I imagine it?
So I think the way I think of it, that might be not the best way. So I think a lot of it as in a parametric regression problem. So basically you say my function is a1 phi1 of x plus a2 phi2 of x, something like that. And now basically the nice thing is that if you have this Mercer decomposition, then these functions are orthogonal, and that means they're not redundant. Okay,
Yeah.
and now if you do this parametric regression, you would probably penalize these coefficients, right? You would say, I would rather not have huge coefficients, but somehow small. And the eigenvalue of the Mercer decomposition basically rescales these coefficients and therefore like changes which functions are easy to learn.
Yeah.
There's also one example in the appendix where we, for a very simple kernel and simple distribution, actually explicitly, like for this cosine kernel, derive these eigenfunctions. So if you want to look at that, that might be instructive.
Yeah, thanks.
Okay, so as I said, the spectrum is quite important, and we'll basically now I will basically show a result that tells you, independently of the function, if your kernel is bad, you will not be able to learn. And therefore, again, I will now focus on pure state encodings, such that k of x is 1. So I think it's not important that our computer is like not noisy or something like that. It's just for a mathematical framework. But you could also do everything with assuming that k of xs is 0.5 or something like that. So that's not important in a physical sense. And in this case, we will also have that basically the sum of these eigenvalues is 1. Okay. And now we'll define the mean density operator, and that's basically the encoding of a single point, and now you average over all points in your distribution, right? And I think for physicists, it's clear that this will be a mixed density operator in general, right? It's not going to be a pure state anymore, unless the encoding is very boring and maps everything to a single quantum state. Basically, that would be a constant. Okay, and now we basically can derive a bound on the largest eigenvalue of our kernel integral operator. And this is basically that the largest eigenvalue is bounded by the root of the purity of this mean density operator. So that means that if your embedding basically, like, let's say, covers your whole Hilbert space in some uniform way, then this purity will decay exponentially with increasing system size, and your largest eigenvalue will also be exponentially small. Okay, and that's the spoiler down here. If that's the case, then it will basically be impossible to learn with non-exponentially much data. Okay, and for a theoretical analysis to basically construct such an example where this goes wrong, we again assume what I said before, that basically we have a d-dimensional problem and we encode every coordinate in a single qubit. And we will additionally assume that the distribution over these axes factorizes. So basically every single coordinate is independent of each other. And we do this because then we can just say that, okay, now the mean embedding is also basically factorizes over the individual qubits mean embeddings. Mm-hmm. And this gives rise to this theorem, which basically tells you that, okay, just recall for a second what the solution is of this kernel-rich regression. And now assume that as we grow D, every single of these mean embeddings for each qubit is upper bounded by some purity delta, okay? So they are just bounded away from 1, that's important. And this will hold for all that we will add. So that's kind of how we describe how this problem scales as we increase the dimensionality.
The scaling assumption is basically just a gap, that no matter what, there's a uniform upper bound in I that's bounded away from 1.
Exactly, yeah. And okay, and now we basically also say how can the sample size vary as we increase the dimensionality of the problem, and we'll say we'll only consider sample sizes that grow at maximally polynomially with the number of qubits. I guess that makes sense. So fix any real number and just assume that the sample size is smaller than d to this number. And what we'll tell you now is basically then we can always find some dimension d0 such that above this threshold we can basically not learn anything. And with not learn anything, we mean that no matter how we regularize, so for any lambda, we have with high probability, so if you choose epsilon small, that basically the true risk of your empirical risk minimizer is almost as bad as just the 2 norm of the target function. Okay, so what does this mean, 2 norm of the target function? You can basically think of the 2 norm as of the target function as the variance of of your data, right? And if your loss is basically almost as bad as the variance of your data, that essentially means that you didn't learn anything, because then you could also just as well say, well, I've just output a constant all the time, and that's as good as that. Okay. So basically, what does this mean if you turn it around? I mean, this purity argument kind of means that if every qubit encoding is somewhat expressive in the sense that it covers some space of the quantum Hilbert space, and this expressivity is basically, let's say, lower bounded, then we will have an upper bound on the purity, right? So I cannot just like increase the expressivity ever more, because if I do that, then I will have to use exponentially much data. And maybe let's illustrate this a bit with a picture or give you some intuition of why this happens. Basically, if you look again at the solution of kernel ridge regression, then it's kind of somewhat a regularized inverse of the kernel matrix. And now what happens, and for this you have to go through the proof, basically is that if the largest eigenvalue is very small, then with high probability, the kernel matrix is basically the identity matrix, okay? Now think of the kernel matrix as the identity matrix, then this term here is just 1 identity plus lambda identity. So basically the coefficients will just be basically given by yi, maybe 1 over 1 plus lambda. And since the kernel matrix is basically 0 on off-diagonal elements, it also means that the pairwise kernel evaluation is basically 0 if we're not evaluating on the same point. And so the function that we will find will, now this is obviously an artistic interpretation, will roughly look like this. So we will fit the points that we saw, but everywhere else essentially will output 0. And this also explains why the loss of this function is close to the 2 norm of the target function. So that's just because the loss of the constant function is exactly the 2 norm of the target function. And the function we learned is actually not so much different from the 0 function in L2 norm, okay? So basically we just overfit because there's too much expressivity. And if you crank up the regularization, this doesn't change much, because essentially what now happens if you crank up this regularization, you will just not exactly fit these points, but have these spikes a little lower, but it won't make it any better because there's just still too much expressivity. Okay, let's have a first look on this like toy experiments that we did. So what did we do to simulate this? Basically, we encode these single dimensions of our input data into d qubits, and then we apply some random unitary operation on all qubits, and then we measure some observable on the first qubit, and that basically defines our target function. Okay, that's how we generate artificial data. We just take these functions and we maybe add some noise. So here I add noise of variance 10 to the -4. Again, this is like run on a classical computer, no measurements involved. That's just a perfect simulation. And then we take this kernel. For the kernel, V doesn't matter because whether you or not you have V there, you basically cancel out. If you do like, if you compute the kernel, then by the cyclic property of the trace, you basically just have unitaries that cancel each other. I think it's interesting because obviously like our kernel is expressive enough, right? It basically is derived from exactly the same structure as the problem, so it will definitely contain the true solution. Now, sorry, that's a bit messy here maybe. Just look at the yellow lines with the crossed marks. Okay, okay, maybe one more word to the setting. I basically keep the problem constantly difficult in the sense that I always rescale the variance of the data, and I always use the same number of data samples for each each step. So with few qubits, this kernel learns perfectly. But then if we add more qubits and the problem becomes more complicated and the kernel more expressive, what happens is that the training error actually goes beyond what is actually possible. So we overfit, but the test error goes up. So this is basically a generalization gap. And 10 to the 0 is basically the worst thing you can have in the way we generate the problem. Okay, so quickly, this kernel overfits. We cannot learn because the eigenvalues decay too fast, even the largest eigenvalue. Okay, so that's kind of this quantum no free lunch story. If we have a quantum kernel that is too expressive, then we won't be able to learn. And maybe let me tell you that this is not just because we did this weird product structure, but this generally happens. If the purity of your mean encoding decays exponentially, then you can basically show the same thing. Also, if it's not a product structure. Okay, also here, if you want to have some questions, that's maybe good.
Yeah, good. Our question. Fully convinced why the mean encoding is so important, because it can tell us that out of the family of kernels we chose, many of them are bad, but like even if like a measure 0 set was not bad, that would not be captured on the mean encoding, but there could still be like a big parameterization of good things. Or said otherwise, how do I know that the encoding concentrates around the mean?
I'm not sure if I get your question, to be honest.
So maybe I can say it differently. We give a lot of strength on like this mean encoding.
Yeah.
But if I write the the pointwise probability of each encoding happening, it could be that the mean encoding has 0 probability. Could be like
yeah. So maybe let's put it differently. So the mean encoding here is only important because I assumed in the beginning that each point gets encoded into a pure state. Okay. Yeah. And now the mean encoding basically allows me to give a kind of an idea of how well did I cover my whole quantum Hilbert space. So think about a single qubit and the Bloch sphere. Now, if your mean encoding will be now the origin of the Bloch sphere, then you know that somehow your data points got mapped on very diverse points on your Bloch sphere, right? So maybe they got mapped on 1 and 0 state. But if your mean encoding is now a very pure state, then you basically know that every data point gets somewhat mapped to the same region of your Bloch sphere.
Yeah, okay. I got it now.
Okay, cool, great. All right, then maybe let's continue. Otherwise, I think we'll also run out of time. Okay, so I guess we're not the first ones to realize that expressivity can harm, and we're also not the first ones to realize this in quantum machine learning. So also there was this paper by people from Google and Robert, I think, who was an intern there. Also a nice paper that definitely also inspired this work. And kind of one way they propose is to use projected quantum kernels. And in rough words, this somehow means that, okay, you don't compute the full kernel, but you kind of reduce the expressivity by computing the kernel on some lower dimensional representation of this quantum state. And we kind of picked up this idea also by construction of our experiments. You basically see that this function, the target function, can just be expressed in terms of the reduced density operator of the first qubit, right? And the full kernel doesn't work. And now our idea is, that's why we call it a bit differently, is we call this biased kernel. Now say we compute a kernel only as the inner product of this first qubit reduced density matrix. Now, what's the idea behind that? If the unitary V is sufficiently expressive, then computing this reduced density operator will be hard, but it's low dimensional. And so basically the learning problem will be super easy because there's only very few parameters, so to speak, that we can actually fit. But it contains all the necessary information about our target function, right? And this is kind of the way I think of this quantum advantages possibly. If you know that your problem was defined in such a way, but you cannot simulate V classically, then basically using this quantum device gives you an advantage in this learning theoretic view. Okay. Now let's look how this works in practice. So Q is this biased kernel that basically always has the same dimensionality of the RKHS. And what we see is that this kernel always learns perfectly the target function. So 10 to the minus 4 is the best we can hope for, because that's just the variance of the noise that I added, and we will not be able to get rid of that. And also you see that training performance and test performance are basically, they coincide. So it just has the perfect capacity. I think worth a look is also this QW. This means biased kernel on the wrong qubit. So basically the same thing, but use the second qubit. And okay, for the case d equal 1, it's actually also the first. But for the case d equal 2, you already see this doesn't learn anything. And curiously, it does not overfit, right? So remember that the full kernel overfitted. And overfitting means that the training error is very low, but test error is large. This wrong kernel actually underfits, like has no means to interpolate the data. And therefore also the training error is basically completely bad. Okay, and that means that I think generally, maybe I'm also not understanding it well enough, this projected kernels, my impression is that just like randomly constraining your functions again in your RKHS will not help you, because basically if you don't know in which corner of your RKHS2 or corner of your quantum invariant space to look at, then yeah, it's just as bad as not constraining it.
But you would surely say more about like the necessity of having a priori knowledge about the type of constraining that's good, right? Is that something you will say, or?
Yeah, no, not really. I mean, I'm basically mostly saying like, when will it not work? At the moment, I don't know any sufficient conditions, so to say, for when you will have this advantage.
But I mean,
but maybe, yeah.
Like this issue of like kind of analyzing the correct inductive bias from a data set, it's a problem that you have classically too. I mean, you have to make a decision about which kernel you choose. I mean, the way I interpret this, it's like there are things that you can do in which it might be good, the same way we know that there are classical kernels that sometimes work. And I mean, like sometimes you know something about the process which generated your data, and this gives you some insight into which to choose. But I feel like you have the same problem. Like here you have the problem of choosing a subspace of the Hilbert space. And it seems like equivalent to me to the process, to the problem of choosing a kernel classically, when you don't have any prior knowledge about the process that generated your data or something like that.
Yes. I totally agree that you have this problem also classically.
I was tempted to ask the same question when you showed the slide at the very beginning, indeed.
But I mean, the problem is now, so I think there's, okay, we have some section about this in the paper that is pretty weak, I would say. But usually in, let's say, classical machine learning, you favor functions that are continuous, okay? And then there's very hardcore statistical literature that tells you that under some continuity assumption on your function, you basically have optimism about your problem, then you cannot substitute. But I think the point is that quantum computers, like usually, like when we sell them, we say that there's something that is substantially better, okay? No, I'm not saying that there will never be a quantum circuit that works somewhat better for a problem. But I think that if you want to have a quantum machine learning model that basically has a substantial advantage, then you really have to have a strong inductive bias that also you cannot encode classically. But I think maybe that's a good point for the discussion at the end. I think maybe there's not much left, so end up in the end. Okay, so I think we have illustrated that all of this works the way with this biased kernel. We can basically learn something, and I would say now, I will tell you in a second that we cannot use this biased kernel, but if we could use, then I would be pretty sure that basically we could also prove that this is a quantum advantage, because the function is just like getting very, very complex with D, and then yeah. Okay, well, we keep this question for the end. And now just quickly, that basically this very trivial example here, I think it's nice to illustrate these learning theoretic perspectives, but completely how well do we need to, or like to evaluate the kernel. And the problem here is that this V unitary is our data, and matrices, then basically with very high probability as D grows, this reduced density matrix fully mixed state. And that also means that the kernel now basically is almost constant, and fluctuations around the constant are of basically exponential small nature. But now if all the relevant information is in this like exponentially small fluctuations, then we need exponentially these tiny fluctuations. But currently, even defining this function, like even defining the data points that I told you for this problem, f of x, if rho is a completely mixed state, and this will basically almost be constant, this function. And yeah, we will already need exponentially many measurements. Can't make this a bit formal. Basically, that's just what I said in formal language. The density operator will be very close to the density mix. And then we also on eigenvalues. And here you have to be a bit careful that there's some caveat here. Don't actually do this for every single deviation over V. And basically something that is not to make a statement about every single V with high probability, you would have to consider, okay, what's the variance? And if that variance is small, then you basically know that with, okay. But basically what it predicts is that we'll have one eigenvalue eigenfunction that is basically one qubit, and the other is exponentially. And of V. And that's basically, again, the of everything important or interesting. The first eigenvalue is the constant of that one we can also learn classically. Yeah, that's just this third main message. Don't forget to measure. And that's what I kind of mean, right? If I estimate each kernel entry to precision 10 to the -3, then this is not a precision that you need to solve the problem with the dimensionality of the problem that you consider. Okay. And so basically, like how to find a quantum advantage in general. So I think basically we have some kind of necessary conditions. So the first one is that the computation that you do, otherwise you could simulate it classically, how your encodings have to be somewhat localized in your quantum Hilbert space. Because if you just consider everything in your quantum Hilbert space, then you will not be able to learn. And so such that you basicalization of your embeddings, you need some prior knowledge, right? Because without prior knowledge, you will probably use an embedding that localizes somewhere completely off topic. And obviously, if you pick this localization randomly, since your quantum Hilbert space is so large, you will almost never pick the right one. And the third thing is to have to be able to measure things or estimate things efficiently. I think everything around the completely mixed state is not a good idea because there you'll have to measure so often. So you basically have to keep some coherence also if you want to use that. Okay, so I think this is mainly kind of negative results, but I think it's cool that we have basically this paper that I mentioned before, this IBM paper. In that paper, then you will basically find that kind of all these things are actually fulfilled there. It keeps coherence, or it's like very, I don't know if coherence is the right word. Namely that the problem comes from this discrete log problem, and they also ensure that you don't need to measure exponentially often. And so for me, that kind of goes back to this question that we had in the beginning quickly. If we know already about some quantum advantages, generally like outside machine learning, I think can use this to create advantages. But at the moment, I'm not sure how to do it without knowing that the problem already in this class of problems. And also, I should definitely think more about what it means for NISQ devices. That's something that is, at least in this work, totally underexplored. Okay, and with that, I'm happy to thank you again, and also thank my collaborators. And yeah, I always need to include this picture of the nice view from our balcony at the Institute. Okay, now I have time for discussion. I don't have much to do else today, so feel free to ask as much as you want. Jens already warned me that there will be a lot of discussions and questions.
Okay, thank you very much indeed. That was great. Wonderful. So we had lots of questions along the way. I'm sure there's more questions.
Yeah, I don't really have a question other than outside of yours a lot. I think you summarized what people know and what people need to do perfectly, but I also feel it's absolutely completely unknown processes that generate classical data sets. You have any insight, I mean, even how to like formalize the notion of like a quantum versus classical advantage. I mean, there's only like certain places you can even do that, like cryptography or Boolean function analysis, and papers example of, I mean, one thing I disagree about a bit in this group is I have this comment a bit offhand, like, whenever there's a quantum advantage in like a known setting, you can make a machine learning problem out of that. I don't think that's something. It's the case that for any sort of decision problem, for instance, where you could get a separation between quantum and classical algorithm, I think there's work involved in trying to figure out how to embed a quantum classical separation from some area into a learning problem. I think that's why that paper is like, however long it is, it's not immediate.
You mean this one?
Yeah. But, I mean, maybe that's an interesting first step in like trying to figure out how to go from the ability to encode kind of specific problems into learning problems from like to the step, this was Johannes's idea basically a long time ago, like to how to encode like any generic complexity separation between complexity classes into some sort of separation between learning algorithms for certain types of problems.
I have a, sorry, I didn't want to.
Yeah, I'm not sure if I can answer or like can respond to that. I mean, excuse me if I was a bit like too general there. That was maybe a bit like hand wavy, these arguments in terms of like, if there's something that we know that there's a distinction, then we can just use that. I agree. I think this would be a promising avenue if you're just up to like writing up a problem that gives some decision or like some distinction between classical and quantum.
Yeah, I mean, I think you're totally right, and like I think I agree with your sentiment completely. But I think something basically, I don't think people have formalized that intuition yet. It's probably a way of like broadening the space that you can look for advantages, like away from like discrete logs, which is basically the only example.
I think also in this regard, I think it's very interesting because the way we need to think about this when we talk about quantum advantages is the way that no classical machine learning people have thought about hardness of machine learning, because they usually don't consider problems that kind of have this weird behavior that we have to make them more complex as D grows and stuff like that. So I think, and usually these learning bounds are fixed. Problem, and then you kind of let the sample size go to infinity and look how well we want to have the complexity and the sample size somehow in some limit increase.
I mean, I totally agree with your point there, and I had to convince myself a long time that it's like meaningful to think about. I mean, for Hamiltonian learning, like it's very obvious what that means is all Boolean functions, like disjunctive normal forms or whatever. It's super clear what the family of data sets. It's not clear, although like I think I'm now convinced that it's natural. For instance, with images, you can think of increasing the resolution systematically as like, and that's like the pixel size. Like there is a real notion of scaling there, or like in financial data, you could include more and more assets. And I think it's not always natural, but I think I think it's meaningful to think about scaling even for these problems, even though people don't typically do that.
So I think there's also like, let's say more in the statistical literature, they consider these problems. So I don't know, consider Gaussians, like standard Gaussians with like increasing dimensionality that only differ in one dimension, and then the problem becomes harder and harder and harder. So such stuff somehow exists, but I think it is like, let's say purely machine learning literature, it's rather rare. Do you mind if I quit my screen share, because then I can actually see some more of you?
Oh yeah, sure. Yeah, of course. Yeah, some people have to move to another meeting, so there's a bit of a collision with a meeting with our Xanadu people, but a core crowd is still there, and then we will recap also later.
Yeah, I'm also sorry for the delay in the beginning. That was totally my bad.
Don't worry. Frederick?
Yeah, I was just wondering, do you have do you have an opinion or an idea about like whether we can learn something from these imported learning advantages? I mean, I think it's great that people work on like deriving learning from known advantages, but I'm wondering like what's to be learned there, or like what's the lesson in order to get the learning, the theory of learning.
So I think,
I mean, maybe to just to add, I mean, what you like your last slide is probably at least one of those things, but then I'm wondering, like, is there more specific details from these papers to be learned?
So I think one interesting thing for me, at least, is that this measurement problem can be handled. So there are settings like these toy settings where it suffices to like estimate the kernel entries with some precision, and this precision does not get arbitrarily bad. So I think that's, for example, cool. And yeah, but other than that, I mean, to me, it's just like on the high level kind of means that you really have to know something about the problem in order to like, or like you have to know that your quantum computer can do something that you otherwise can't, kind of, right?
Yeah, which I mean means kind of, if you find some learning advantage that hasn't, like, that is not derived from anything, you would, I mean, that's a question, is would there always be the converse conclusion to, like, would there always be the conclusion the other direction? that you, whenever you find something like this, you would always be able to also create or like pose just a conventional computational problem where you also have a quantum advantage.
I guess that's a kind of like a complexity kind of question, right?
It's kind of a Ryan style question.
Yeah, I mean, I think that I think that the answer is there would always be a cryptographic application of a learning problem that has a separation, in the sense that like many of these separate, in some sense at a very high level, you can view, like imagine you have a cryptographic primitive and now you have some like attacker. Basically the attacker is in some sense like getting access to a data set, which is defined by some primitive. And like the reason you can use cryptographic proofs to prove learning separation is a proof of the fact that any person who can get data from some source has to look at that and exponentially many times before they can learn something. Like in essence, like when people were laying the foundations of crypto, they were like simultaneously laying the foundations of computational learning theory. And so I think that like if you found some interesting classical data set for which you could prove some quantum classical separation, I think you would immediately get some sort of cryptographic primitive. Yeah. But I also have to say, like, about this issue of what can you learn from these papers, I think that these papers, like this one from Srinivasan and Kristen and these guys, weirdly enough, I think they interpreted almost completely wrongly by the community. I wonder how many I wonder how many of the citations to that paper say, now we know that we can like get a quantum advantage in learning. Whereas like the way I interpret it, it's like, that's how hard you have to work and how much structure you have to embed to get an advantage for learning. And given that, like, okay, it's true that you can never learn unless there's structure. Like that's also something people don't appreciate. But like we know that there's only so many structures that quantum algorithms can employ, like hidden subgroups, for example. And like, I think the message of those papers is like the exact opposite to how people interpret them. It's not like, oh, wow, quantum computers can get an advantage. It's more like, look how incredibly structured these problems have to be in order to get an advantage. And that means it's like unlikely to get advantages for structures like, I don't know, sequential generation of data via a Markov process or something like that, which is the type of data that people normally have in real world applications. Yeah. So I think you can learn a lot, but it's kind of like the opposite of what people are actually learning from it in some sense. Yeah.
So the mission, I just remembered that there was like some paper I didn't read, but I read the title, which is probably relevant to your question, Frederick.
Yeah.
We'll put it in the chat. I think this is like, okay, if a little bit of the type, if you can efficiently learn this stuff, then you would get some separations back down, stuff like that. So I think they also will be relevant. And share Ryan's sentiment. It's entirely unclear why like naturally occurring data should be amenable to like quantum machine learning models. Anyhow, and the only thing you want to hope for is like if there's some quantum stuff involved, or at least then it might be sufficiently obvious for us to see it.
I mean, maybe like a way to think about this is to take inspiration from, for instance, like what's a class of models I often think of as being like extremely obvious what the inductive bias is, hidden Markov models for distribution modeling. Because like many processes in nature, they're sequential, like speech, like text, like you get one thing and then you generate the next state, et cetera, et cetera. And that's like the direct inspiration for these probabilistic graphical models. You know they have the right inductive bias because you know what the process that was that generated them. And I don't know, maybe there are sort of, I mean, maybe that's the kind of thing where you could like take circuits and measuring ancillas and then getting the outputs of those. And through this way, you create sequences, and maybe they're not kind of realistic. I mean, they're not corresponding to text or things like this, but they're at least like, I mean, maybe you should start by like understanding the process that generates the data and then building models around those. But then like you have no tools to prove advantages. I think this problem is super hard to move beyond the state of what people already know, actually.
So I think something that could also be kind of cool, like in this Niskish approach, to think of like how can we make something there? Like how could we generate a data set on a NISC device that we could then learn again good with this NISC device, but have a hard time to learn with some other device. I mean, that's kind of what we tried, right? And then we realized, shit, that naive way does not work. So you would have to kind of come up with a circuit that still kind of has a peak measurement distribution, right? Like that. So you have to make a complicated computation along the way, and then a very, kind of.
This is kind of more or less exactly what a lot of us have been thinking about really hard for the last year, I would say. And what we can now show, and like we'll put something out in the next like weeks, hopefully, is that super surprisingly, the output distributions of local quantum circuits are hard to learn even for quantum algorithms. Like, and this is kind of like exactly the thing that you were saying you would hope would be true, because you know that these are hard to classically simulate. And so like you would hope that quantum learning algorithms could get an advantage for that problem. And yeah, I mean, to be honest, I'm quite excited about that, because I totally agree with you that that was like the natural thing to look at. It's like you already have some like hardness result from simulatability, and there's this hope that, well, maybe a quantum learning algorithm can do it, but
that's not the case.
Yeah, it's not the case, like with some caveats, and like there's room to move, but it's like, yeah, I think it's not so easy, basically. Yeah.
Indeed. Also, when
I also have to drop out now. Thanks a lot for the talk, Jonas.
See you, Jonas.
See you guys.
I also have to drop out. Thanks for a really nice talk. I think it's a great paper, and it's really cool to hear your perspective.
Thank you, Ryan.
Yeah.
Okay. So when you say that it's when they say it's a rigorous and robust quantum speeder, but they mean like robust against additive errors in the kernel entries, but that's a very specific way of being robust, right? I mean, that's perfectly compatible with the intuition that all one can hope for is to find advantages when there's kind of something quantum in the data given already, right? So that one can relate the learning advantage to a computational complexity advantage in the problem, right? That's all they mean by robust.
Yeah, I think robust, they mean kind of like to the statistical error induced by measurements. But it's certainly not robust to noise in your computation, like in your quantum computation, right? Like hardware noise. That's definitely not what they are robust to, for example.
Okay. And I mean, in the slide you showed on this barren plateaus and kernels, I mean, you look at like hard distributed unitaries or isometries. Of course, well, then you have all this like Levis lemma intuition coming in and so on. Then you show what you show, but how reasonable is it to pick Haar measure distributed V's in the first place?
So okay, let me think. So yeah, I think the point is if it's not Haar measure random unitary, then you would probably pick a unitary that does some cool stuff, right?
But then you're back to the same problem. I mean, of course, I mean, a Haar measure is like Drain's principle, like if you don't know anything, that's what you have to do, and then you get the concentration of measure result. Otherwise, you would say, what structured V would you take in the first place? And then you're back to square one. Indeed.
Yeah, so I mean that's exactly the point, kind of. I think also somehow some bottom line of this work is if we just do random stuff with our quantum computers, like it's not gonna work. We kind of have to do computations that have some structure.
I mean, this is like, of course, a super interesting bottom line of all this and message. I mean, this is like in some way there's a kind of a mirroring of the many years of work on quantum algorithms design, where people were super excited that quantum computers would be supercomputers that would solve any kind of interesting problem that comes to your mind. And then, I mean, the long and winding road, or the outcome of that process was that, yes, that's kind of true, but you need extremely specific type of data, specific type of structures, and then you can hope for something. And that was always got built around a small number of ideas, like hidden subgroup problems on the one hand, and then there was a long silence, and then people thought, oh yeah, but quantum computers can exponentiate matrices well, so that you can do e to the power of sparse, e to the power of low rank, or so positive low rank well, and then there was this HHL and SDP type rush, and a bit of quantum walks and so on. But these were like key ideas, and whenever there was an idea, there was an algorithm, but it's never the other way around. I mean, that's also how people approach quantum research, as saying, oh, I have a water supply problem, or like some scheduling problem. How can you do that? And this is never like that. And in quantum machine learning, there is a bit of a similar like development happening, in that it's just not obvious to do anything if you can't exploit a given structure. Even though that's even less obvious, because there might be an advantage. It's just you wouldn't know how to prove it. So in some sense, there could still be the outcome that I mean, large-scale quantum computers just do something. Whereas in a common problem, you need to have the structure to get the algorithm running. In the methods you propose, I mean, it's just that you need to have a priori knowledge, but it could still be that heuristically, they work much better than you think.
Yeah, I think like empirically, I mean, I can imagine that there's something where I run this on a quantum computer and it gives me better outcome than I get on my classical computer. But I don't think that I could, like, at the moment, scale this up basically to make this work even more on a larger problem.
No, indeed. I mean, no, I couldn't agree more. Also, I mean, like, also your sentiment is like very much along the line of lots of, I mean, the work that Ryan mentioned along this like similar lines. I mean, of course, we look at like quantum classical learning, the output distribution of random quantum circuits with like followed by local measurements, where there's also like a negative statement coming out at the end of the day, and that's interesting because it kind of challenges where to look for new things. So that's extremely important.
Yeah, I think it's also interesting to see this kind of, I mean, in the beginning, where like when I first read about this variational quantum eigensolvers and work like this, I was like sounds a bit like magic to me. Like, I don't really understand why we should be lucky to, I don't know, use the right parameterization and stuff like that. And also like this idea that, yeah, maybe noisy intermediate scale quantum devices are good for machine learning. Sounded a bit like, yeah, okay, maybe, but I don't see why. And yeah.
No, I mean, it's still, I mean, that claim is still standing, right? I would say. I mean, of course, kernel methods are very specific reading of that. And I mean, you say this yourself. I mean, the idea that you just embed stuff in huge dimensional Hilbert spaces and hope for the best, I mean, that's of course marked by all kinds of problems. And I mean, like the kind of statistics problem is only one, but then, I mean, you bump into the problem that you just need so much structure in your problem that it's just unlikely that you throw any data on this and then you would get any advantage.
Yeah, I mean, I think it's yeah, let's see what comes out of these quantum neural networks and variational stuff. But I think that, I mean, I'm not so optimistic that anything will work much better if you do variational quantum methods for machine learning. Like, I mean, of course, like neural networks empirically, classically outperform kernel methods on some tasks. But I think that's more, the reason is more that it's like, okay, they have cooler architectures, they great hardware and stuff like that. And I think it's not such a conceptual thing that they are just like conceptually so much better.
No,
so But yeah, I mean,
agreed. But then it's still true that kernel methods are in some way special, and there's like I don't know. I mean, if you think of just plain vanilla parameterized quantum circuits, then I mean the setting is somewhat different, and you would also presumably need different structure to get going. Well, although on some level they're even harder to analyze. I mean, as you know, we had this work on generalization bounds where you can say something on generalization, but again, it doesn't really say so much on what type of data they perform well, which would be, of course, very interesting and very good. But that seems to be the big question. And what you say, I mean, on the IBM paper is really interesting because it's really interpreted somewhat differently. But that's also because people want to see this happening, and I think it's good to look for positive and negative results. Besides, by the way, also the paper we did on park distribution learning, on like thinking of how to get generators that are in the probably approximately correct sense, spitting out new samples from a meaningful concept class. Of course, again, the concept class is meaningful and well defined and everything, and it's a proper exponential separation, not in sample complexity, but in computational complexity. It's wonderful. It's a true full exponential gap, and like we are super happy, super proud. That said, ultimately, of course, it's a concept class that again makes use of an interesting quantum structure. So I mean the hard work in the like down there in the machine is coming from discrete logs. So we are like basically there's the hierarchy, what we do and how this is being broken, but this is basically using like a hierarchy that's breakable by the discrete log as a one-way function. So again, in a quite similar fashion, we get a kind of a quantum advantage, yes, a different one, not a sampling, but a computational one, but again coming from a quantum computational problem. No, it's good. Yeah, it's interesting. That gives lots of food for thought. That's cool. I love it.
Yeah.
It's really the right.
Yeah, I'm also really excited to go back to it. It was very unfortunate timing that I worked on this and then moved to the internship, where I now for 4 months have to do like just classical causality